Ever wonder how engineers can predict exactly how a rock shatters? Or, how a concrete wall just crumbles in an earthquake? It's a seriously tricky problem for simulations. I mean, how do you model something that starts as one solid piece and then explodes into a bunch of flying fragments? Well, turns out there's a brilliant method designed for just that, and we're going to break it down for you. All right, here's what we've got on tap. We'll kick things off with the big simulation problem itself, then we'll meet our hybrid hero, FDEM. After that, we'll pop the hood to see how it actually works, check out where it's being used in the real world, and wrap it all up with the one key thing you've got to remember.
Okay, let's dive into Section 1. So, what's the big deal? Why is simulating something breaking apart so tough? Well, it really comes down to the fact that the material basically changes its whole identity. And most simulation tools, they're just not built for that. They're specialists, not all-rounders.
So let's chew on this question for a sec. Just picture it. You've got a rock in a lab. At the start, it's just a rock, a single solid block. You start squeezing it, right? It deforms a little, but it's still one piece. But then, bam! Cracks start to form. And suddenly, it's not a rock anymore. It's a pile of broken bits. You're dealing with two completely different worlds, physically speaking.
And this is where we meet the two classic tools of the trade. First, you've got the finite element method, FEM for short. It's absolutely brilliant for figuring out stress and strain in stuff that's still in one piece, a rock before it breaks. Then you've got the discrete element method, or DEM. This one's perfect for when things are already broken. It tracks all those separate little blocks bouncing around and colliding. That's our pile of rubble after the fact. The problem? Neither one can tell the whole story, from start to finish.
So, how do you possibly bridge that gap? Well, you bring in a hero, a hybrid hero to be exact, and that is precisely what FDEM is. It's a method that was basically invented to solve this exact problem by smashing the best parts of both worlds together. Okay, so here's the textbook definition. The finite discrete element method, or FDEM, is a hybrid method that simulates that entire transition from a solid object to a bunch of separate pieces. The best way to think about it, it's like a hybrid car. It knows when to use the electric motor and when to fire up the gas engine, right? It just seamlessly switches to whatever's best for the situation. FDM does the exact same thing, but it's switching between physics models.
And honestly, no other method can really do this as naturally. That's the key, because FDEM was literally built from the ground up for this one job. It can handle the entire life cycle of a fracture. We're talking from the very first microscopic crack all the way to the final pile of dust, and it does it all in one seamless simulation.
All right, so how on earth does it actually pull this off? Let's pop the hood and take a look at the three key ingredients that make all this magic happen. And don't worry, I promise we'll keep it straightforward. First up, component number 1, the finite element part. So when the simulation kicks off, the material is basically a mesh of tiny, interconnected triangles. These triangles do exactly what they do in a normal FEM analysis. They calculate how the solid stuff deforms and how stress builds up when you put it under load. This is what we call the continuous phase. Now, component 2. This is the secret sauce. This is the clever bit. In between every single one of those triangles, FSDEM sticks these special little things called crack elements. Think of them like an intelligent glue holding the whole thing together. And this glue has a rulebook based on stuff like tensile strength and cohesion, and it's constantly checking the stress. When the stress gets too high, the glue decides, all right, it's time to break. This right here is the absolute heart of FDEM. And that brings us to component number 3, the discrete element part. So what happens when that intelligent glue finally breaks? Well, the triangles that were once connected are now set free. They become their own individual blocks, or discrete elements. And from that exact moment, the simulation completely shifts gears. It starts treating them as separate things that can bounce off each other, slide around, and rotate, just like a standard DEM simulation.
Okay, so let's walk through that whole life cycle one more time. Step 1. Everything's intact, and the simulation is basically running in FEM mode. Step 2. Stress starts to build up, and those little crack elements start thinking about breaking. Step 3. The cracks start to spread as more and more of those elements give way. Step 4. A chunk breaks off completely and becomes a new block, and boom, the simulation kicks into DEM mode for that piece. And finally, step 5. All those new blocks start interacting, colliding, and settling, all governed by DEM physics. That's the whole story, from solid to rubble.
All right, so this whole method is obviously super clever, but where do people actually use it? That's what we're getting into now, the real-world applications. And trust me, they're every bit as cool as the theory.
And the range of uses is just incredible. I mean, engineers use FDEM for everything, from simple lab tests like crushing a rock sample, all the way up to massive, complex engineering problems. We're talking predicting landslides and slope failures, figuring out how rock is going to fracture when you're digging a tunnel, optimizing blasting patterns in a mine to get just the right kind of fragmentation, and even simulating hydraulic fracturing. It's super versatile. Of course, to run one of these powerful simulations, you can't just press go. You've got to feed the model some key info. You basically have to answer 3 main questions. First, what's this material like before it breaks? Those are your elastic parameters. Second, what are the rules for how it breaks? That's your fracture parameters, things like tensile strength. And third, you need a few numerical inputs just to make sure the simulation runs smoothly and doesn't, blow up.
Phew! Okay, we have covered a ton of ground here. We've talked about the problem, how FDEM works under the hood, and where it's used. So now, let's just boil everything down to the one single idea, the key takeaway you should walk away with.
So if you're going to remember just one thing from all of this, what should it be? Well, it's that for all its apparent complexity, the core idea behind FDEM is actually incredibly simple. It's beautiful, really. It all just boils down to one single thing.
And here it is. This is the whole ballgame. Before cracking, the simulation acts just like FEM. But the instant a crack forms and a new block is created, boom, the simulation starts acting like DEM for that block. It's like a chameleon, right? It perfectly adapts its behavior based on one simple question. Is the material cracked or not? It's FEM and DEM all wrapped up in one elegant package.
So there you have it, the finite discrete element method. A seriously powerful tool for simulating the unbreakable right up until the moment it breaks. And that really just leaves us with one final thought, one question for you. Now that you understand the what and the why of FDEM, what complex fracture problem would you want to simulate next?